Verilog coding for a digital circuit can be done either through structural modeling or behavioral modeling. When you have done the Carnot mapping and achieved the digital circuit in terms of basic logic gates, structural modeling is the method to implement that circuit in Verilog. Structural modeling needs some prerequisites which we are going to discuss today. Then we will do the structural modeling of a 4:1 marks and a full adder in Verilog. Then we will verify the functionality of the two circuits using Verilog test bench and Vivado and Icarus Verilog simulator. So stay tuned, stay focused. Hey guys, welcome back. In this episode, we are going to discuss the below points. First, we will talk about the various Verilog methods like structural and behavioral modeling and their subdivisions, what are their prerequisite needs. Next, we will talk about in detail for the structural or gate level modeling prerequisite, which is the gate primitives. Next, we will talk about the structural or gate level modeling of a 4:1 marks with test bench. So we will design the 4:1 marks and also we'll write the test bench to verify its functionality. Next, we will do the structural or gate level modeling of another digital circuit, that is full adder, and we will also write a test bench for it to verify its functionality. Now here I would like to mention one thing. The test bench is a very important part because when you are writing a module, you may not be 100% correct. So the intention of writing a module is checked by the test bench. So the writing of a module in a Verilog is essential, and utmost essential is the test bench because that verifies your design whichever you have written. So with that note, let's move on to the next slide. Verilog modeling methods. The Verilog modeling type is broadly categorized into two major subdivisions. First one is the structural modeling, which has the basic necessities as gate primitives. We'll cover this later in this presentation. The other major subdivision is behavioral modeling. It has two further subdivisions. First one is continuous assignments. The another one is procedural assignments. Now these two are subdivisions, whereas this is a basic necessity which is needed to construct this. Similarly, this and this are the basic needs that you must learn to write the behavioral modeling. So the basic structure of the Verilog modeling is in front of you. Either you can take a structural modeling or a behavioral modeling. It depends upon how you are approaching towards the design. These are two different approaches and you should not confuse one with another. So we are done with this particular slide. Let's move on to the next slide. In today's discussion, we will be focusing on the structural modeling and we will in detail talk about the gate primitives. We are done with this particular slide. So let's move on to the next slide. Structural modeling prerequisite. Structural modeling needs a few prerequisites which comes along with the Verilog language and with the simulator. So the simulator you are using, it has to support the prerequisites. What are the prerequisites? A set of pre-designed logic gates are provided in Verilog language inbuilt library. These are called gate primitives. So let me stress here, this is Verilog language inbuilt library. So this comes along with the language. You don't have to create it. You have to learn how to use it. And these are generically called the gate primitives. So in this kind of library, what you can expect? The basic gates like AND, OR, NOR, NAND, XOR and XNOR. So here are some figures just for your visualization. Generally, when we are writing the syntax, the first terminal is output followed by inputs, and inputs can be two or more. So here you can see there are two inputs, right? You know that this gate can have more than two inputs. So in this fashion, this is written that first one is output, rest of the things are inputs. The next point is we start our example here. This is a typical syntax. This is the primitive gate. You are writing your instance name. Here the first one is the output. So this is the OR gate. Here first you are writing the output and then the first input and the next input. So these two are here, here and here. So this way you write your syntax to use them from the library. Next comes the NOR. As you can see, this one, right? This one is NOR. And here you can see this is green color because this is a reserved keyword. This is green, this is green. So these two are reserved keyword. You cannot use them for your own definition. So these are predefined. So these are coming as green. In different text editor or IDE, you will find this is coming in a different color, maybe in gray or something, or maybe brown. Okay, maybe in some other color, maybe blue. However, these are reserved keywords and you cannot use them for your own module name. Next comes the instance and then the output and the two inputs. Here is a typo. I has been printed twice. Ignore this, please. Next comes the AND. It is also two input AND. This is a two input AND. Next, the instance output first. This one is first and followed by the two inputs. Similarly, you can see that the NAND is also there. This one is NAND. So this one is NAND, right? And output comes first. Here is the output and the two inputs are followed by. So this way you can write the connectivity. So actually, in case this in or out, all these things will be connected by either range or where type of variables. So we will later discuss in some later episode about this type of variables. But first you have to grasp the basic structure of the Verilog modeling so that you can give a kickstart. Next one is a 3-input NAND. So here is the NAND gate, here is the output, and here we do not have the picture. However, you can see there are 3 inputs, in 1, in 2 and in 3. So the output is single. So this is constant. Here it is, you can follow after so many things that first terminal remains the output. So here is output, here is output, output and output, and rest of the things are input. Here 2 inputs, 2 inputs, 2 inputs, and here you can see 3 inputs. Next comes the XOR. It has the similar thing. And next comes the XNOR. XOR and XNOR. These are here. Similarly, these two are outputs and the following ports are input port. So this should be the syntax. You should use the first one is the reserved keyword or NOR and you are very much familiar with these names. So these are very easy things to remember. Next, you can name the instance as per your own nomenclature or as per your company's nomenclature or whatever you find suitable. So these things you will name them. And I will later show you in some upcoming episode what you should do or what you should not do about this nomenclature. So we are done with this particular slide. Let's move on to the next slide. We are continuing our prerequisites here in this slide. Transmission gates. This is buffer and NOT gate. This is a structure of a buffer and this is a structure of a NOT gate. You can see, you can identify the difference. Here you don't have a bubble and here you have a bubble. In NOT gate, this is a NOT gate and this is the buffer. So this is the basic structural difference in symbols between the two. This has one input and one output. However, there can be various different scenarios. One or more outputs first and then single input at the last. So one or more outputs will come first. So it can drive multiple things, right? Here you can have more outputs, right? So output will come first and input will be a single, right? This is the nature. So it is expected single input, single output. However, due to drivability, you can have multiple output ports here. Let us see the example. So this is reserved keyword buff and it is your instance name out then in. Similarly, this one is the reserved keyword. This was the instance and this is out and in. So this is very simple. Next, here we have a NOT instance which is having more than one output and one input. So input here is fixed. As compared to the previous slide, here input is one and output can be many. And this is because of the drivability, right? If this NOT has multiple drivability, right? Here 1 2 3 4, so we have 2 3 and 4. This kind of 4 outputs will be there to drive 4 different outputs. In different circuit configurations you may need them and hence these are kept in the library and you can use in this fashion. So we are done with this particular slide. Let's move on to the next slide. We are continuing here the structural modeling prerequisites and here let me start. Special transmission gates, buff if 0, buff if 1, not if 0 and not if 1. How do they look? They have a different structure. Here it is a buff if 0, right? And here you can see apart from the in or out, we have another control input. So this is a very distinct feature. Next, for buff if 1, we have in and out and we have extra control. So you can see here, let me clear it. Here you can see this is if 0. So it's a 0 logic and we have a bubbled input for the control. And here it is 1. So we have a direct non-bubbled input. Now for the not 1, right? So you can see the not if 0 and not if 1. So this is common, this bubble is there because of the not, and here you can see because of if 0, here it is a bubbled input for the control input, and here the direct control input. So this is a structural difference with a basic buffer and the basic NOT gate. These are tri-state buffer or inverters, output terminals first and then input and then control are inputs. Example, buff if 0. Here this is a reserved keyword, and hence here in this particular slide I have kept the color green for the reserved keywords, and this is your instance name, and you can see here out this one, in this one, and control this one. So this way you have to instantiate the defined gate. Next is the buff if 1. Similar way you can see that reserved keyword, instance name, and out. So this one is out, in, and control. So here is in and here is control. This way you will define the if 1. Similarly you will define the not if 0 and not if 1. So here you can see out remains at the first one, then input, and then the control input. So the basic similarity you can see in the syntax is that for these 4 type of transmission gates, these are special transmission gates, you have the structure in common for the syntax to be used. We are done with this particular slide. Let's move on to the next slide. Now, here in this slide, we will do the structural modeling or the gate level modeling of 4 to 1 marks. Let us begin. Here we write the first line, that is the module definition. Here we give our custom module name, marks 4 to 1, and here we define the different input and outputs. Now we need a picture here. So here comes our picture. So you can see this is the out. So this is out, input 0, input 1, input 2, input 3. Here we define 0, 1, 2, 3. And we have select 1 and select 0. And here we have select 1 and select 0. This is the circuit, and we have defined the corresponding ports. These names you can do set by your own convention, and you have to maintain that convention because you have to remember things later on. In actual VLSI design, it's not that you are doing only a single module forever, because you have to keep on doing it and you have to maintain your convention so that whatever module you have defined 6 months ago, you should be able to intercept it even after 6 years. So your convention should be very much from today when you are learning the Verilog. And in case you are working in a company, there you have some conventions to follow. You have to follow that. That is my additional input for you. Next, we define the direction of out as out, and we define the direction input of all the rest of the ports, because these ports and these 2 ports are input and we have only single out. We type the keyword where here, followed by the different wirings we need apart from these ports. Now, where are these wires? Cell 1N. So here we are wiring this, right? This wire that goes up to this, right? And here it goes up to this. So these 2 wires are defined here, cell 1N, cell 1N. So this is N means the negated. That means cell 1, and once we put a NOT gate here, it gets negated. So it is N is coming here. Similarly, cell 0N, right? Here this is cell 0N, and it goes like this and goes here and goes here. You can see the different wirings. Now there are 4 more here. From these output, the AND gates 1, 2, 3, 4. This will have outputs and which will be redirected to the final OR gate here, right? So these were, and this were. We have to give them a name, and hence we define Y0, Y1, Y2, Y3. And here in this picture, clearly I have marked them, so you can clearly identify. For structural level modeling, as I have mentioned in the intro, that you have this circuit ready with you, maybe with Carnot mapping or POS or SOP method, whatever you have done, you have this ready. So you put these names first, right? These port names, this one, this one, this one, this one, this one, and the wires like this, you name them first in your diagram, and then you start writing this code. So this will be very helpful. It's not that you start writing the code and then you name. That you can do obviously, but it is a good practice. First you name them in your diagram and then you start writing the code. Next, here is the NOT gate. So this is cell 1N and cell 1. So it is talking about this one right here. So here we have started our structural modeling. you can see that we are using a reserved keyword, but there is no instance here. This is another beauty of Verilog, that you can skip the instance name, right? You can directly use from the library and the language and the simulator will identify them. This is very easy to use because here you have to write only the gate name. Here you can see another NOT, which is this one, this NOT gate. It has input cell 0 and cell 0n. So cell 0n and cell 0. At this stage, you can see the primitive syntax that we have learned last 3 slides. Those are coming into use. Next, here we have the AND gate, and you can see this one is the first AND gate. So here we have Y0 and here it is Y0. So this is the first NAND gate. And next, we have the next AND gate, which is Y1, and it is here, the second one. Third one here, Y2, this one, and fourth one is here, Y3. So this part, whatever we are doing it right now, this is called the structural modeling of all these AND gates, AND gates, AND gates, and NOT gates. These we have used from library. So these 4 gates, these 2 gates, and this gate we have used from library, that is from the gate primitives. And you can see here, as per our port definition from the diagram, we have connected them. So output is here, input, and then we have the rest of the input as per our circuit connection. Finally, we have the OR gate here. This one is the 4 input OR gate, and here first we have the out, and then we have 4 inputs. So Y0, Y1, Y2, Y3. So those are going as an input to this OR gate. So you can find the similarity when you have multiple ICs connected in the breadboard. This way you write your circuit and then you do the wiring. So in Verilog, it is very similar way. You are using the library gates here and you are doing the connectivity through this port nomenclature and wires that we have defined. We end our module here. Here we started our module and here we ending our module of marks 4 to 1. This is the multiplexer and we have 2 select inputs, 4 inputs and 1 output. So we are done with this particular module definition and design as per the structural modeling. Now the things are clear to you what is called a structural modeling. We are done with this particular slide. Let's move on to the next slide. Here in this slide, we will design the test bench of the 4 to 1 marks that we have designed. So first we write the module, then marks underscore TB. TB refers as the test bench. And here you can see we have not defined any input output ports because this is kind of like we have your module here design which you have done, right? And the test bench is around it. It's like the breadboard. So the breadboard don't have ports, right? Similarly, the test bench also do not have ports. However, the chip or the IC that you are putting in the breadboard will have ports. Your module will have ports. So this is a very similarity between the breadboard and the Verilog language. Here is our circuit, which we have used in last slide also. I have kept it for your easy reference so that you can relate it. So first here we define reg here, that is register type of variable and where. So register type of variables are used who can store the values with time. So here remember these are for your test bench. That means these are part of your breadboard which you will connect to the circuit inputs, right? So remember this thing. Next we instantiate. That means we are putting a physical chip into the breadboard, right? This is a module name and this is the instance name, marks underscore inst. You can name it as per your own nomenclature or as per your company's nomenclature. So here we have used the port names as is out, input 0, input 1, input 2, 3, cell and 0. So one more thing here in this slide, I have kept the names exactly same. We can vary them in upcoming episodes. We will discuss about that. But for simplicity, I have kept the names same right now for your understanding. We start our initial block. Here the initial and the begin means it is beginning the block. Then we have the system command dump file and we are writing the VCD file name. This you can give as per your own nomenclature. And here when we write the dump vars, that means it will dump all the variables, right? Here all these variable, this dump vars command will dump into this particular file. So this is the purpose of the dump vars. Next, we have the display. It's similar to the printf command. Here I have made 4 tab separated column names for input 0, input 1, input 2 and input 3. These will come as a text output. Then at time 0, this is the delay symbol. I will discuss later in some other episode. this is a delay symbol, at that means at 0 time we have the input defined. So if you put a curly bracket, right, and if you club multiple variables here, you can give a value in one go. Otherwise you have to use 4 different statements to define them. This is a kind of shorthand, and that is very easy for you to write a short and simple test bench. Now let me explain. Here are 4 inputs, and you can see because 4 we are putting number 4 tick B. B means binary, and we are giving the binary values 0 1 1 0. So these are going to 0 is going to this, 1 is going to this one going to 2, and this 0 goes to 3. So this way we are defining them. Next we have the display command. Here we are also using the tab separated value. However, here we use the column names. Here we are printing the column values of input 0, input 1, input 2, input 3. Next we have the next column names for cell 1, cell 0 and out. So these are also tab separated. You can see for a better viewing experience. Next we have the $monitor. So this is a dynamic kind of printf operation which keeps on monitoring these values. If any one of them changes, it gives a printout as per this entire command. Next we have the value giving. So after time unit 1, we are giving the value cell 1 and cell 0 as 2 binary. 0 goes to this one and this 0 goes to this one. This 2 is because there are 2 variables here and B is binary and we are giving 2 values. After next one time unit, we are giving the value 0 to this one and 1 to this one. Next, after again another one time unit delay. So this is adding a more delay. That means after elapse of one time unit and again after elapse of time unit, that means 1, 2, 3. So 3 time unit has been elapsed and there we are giving 1 to cell 1 and 0 to cell 0. Next, after elapse of further one time unit, we are giving 1 to cell 1 and this 1 to cell 0. And then after 5 time units, we are calling the system command finish to finish the simulation. As I have mentioned in previous episode and other previous episodes, that the Verilog is a transient simulation. That means we have an independent time axis with respect to every other thing change, whether we change it or as per the circuit operation change. So the timing simulation has to have an end, and this end is defined by this finish command, and it is a system defined command and it's a reserved keyword, and hence I have kept it in green. You cannot use it for some other purpose. So all these things, right, this dump file, dump vars, display, monitor, these are already reserved keyword. So like that initial and begin, so you cannot use them for your own purpose. So they have a defined purpose and you have to use them for that only. And here we end our initial begin, right, initial block we are ending with end. Then we are ending our test bench module with here. So you can see in the test bench, we have defined or changed our values. In breadboard, what you do physically, you connect, you have a plus output and you have a ground connection, right? And you keep on changing either to this or to that and this to that. Like that, we are changing here. So this is a very similar to the breadboard operation. Now, here we have instantiated a mux. So we are operating on mux. Once our slide ends, we will do the simulation in both Vivado and Icarus Verilog. So we are done with this particular slide. Let's move on to the next slide. Structural or gate level modeling of a full adder. Here we will design a full adder using half adders. Also, we'll write a code for the half adder. In actual practice, you may get this half adder from a vendor and you can use it to make a full adder. So this is another type of structural modeling where you have a predefined block, which is here the half adder, and you are using it to make another design. So full adder circuit using 2 half adder. So this is the circuit and here is the circuit. Here you can see this is a half adder and this is a half adder. So in actual design, we are using 1 for this one, half adder 1, and here this is half adder 2. So let us start. You can see we have defined our basic inputs of the bigger block as A, B and C in, and we have defined the output as sum and C out. So here let us define the half adder module first. So module half adder, and we have A, B and sum and carry. So you can see A, B, sum and carry. This is very simple. We have putting inputs A and B, output word type sum and carry. And here we are using a assignment command here. I will explain in some later episode, which is not part of the structural modeling. It comes in the behavioral modeling. I will explain in those episodes. For now, as this particular half adder is coming from a vendor to you, you are not designing it. However, I am explaining the code. So here we are using an assign statement for the carry. Sum is A XOR B and carry is A and B. And here we end module of the half adder. So this half adder module you have received from your vendor, and using this you will be designing or you will be doing a structural modeling of a full adder. Here first statement is coming here as the module definition full adder, and here you can see we have defined the 3 inputs and 2 outputs, right? The A, B, C in and sum and carry out. Next, we define the type of the ports, input port as A, B, C in and output port as sum and C out. Next, we define the interconnection wire, that is S1, C1 and C2. So these are interconnection wires. This will be using for this circuit. As I have mentioned, for structural modeling, you have already this diagram with you. So you have the diagram first, and as per that, you are writing your Verilog code here. So this must be very clear to you, because the structural modeling fundamentals are like that. You have the design first in your hand and then you are writing the Verilog code for this. So half adder 1, we have the instance. So we have the module definition here, and we are using an instance name HA1. So this is HA1, and you can see AB is here and S1, C1. So S1 and C1 is here. Next comes the half adder 2. We have C in and S1. So C in and S1 as inputs, and we have sum and C2 as output. So sum goes to this sum and carry is connected with C2, the wire, and it goes to the OR gate. Now we have to have the OR gate. So let us introduce the OR gate. So OR gate here has 2 input, 1 output here, C out. This is the C out, and we have C1 and C2. So C1 and C2 as inputs. So here you can see that using library gates, I have made a inline comment here for the good understanding. Now here we end our full adder module. So the definition of the full adder is done here in Verilog, and corresponding diagram is with you. So in structural modeling, the diagram should be ready before the writing the code, and this is here. So we are done with this particular slide. Let's move on to the next slide. Structural or gate level modeling, and here we are writing the test bench to verify the full adder that we have written in the previous slide. So here we start writing our code. Here we write our module and test bench. Since this is a test bench, this is like a breadboard on which you are putting your module as a chip. It do not have the ports, so there is no ports defined here. Here, right, here is our basic circuitry of the full adder, which we are instantiating inside this test bench. So here we type reg A, B, C in. Here A, B, C in, these are reg type. So this can actually over time remember the values, and where cannot remember the values over time. So here sum and carry, these are wheres. I will explain in some later episode about these variables, what are the deep meaning of them. Here we initial and begin, and here we use the dump file to name the full adder.vcd, and dump vars will dump all the variables into this vcd file. Display, here we are using the display command for the column name, time, tab separated A, B, S, C in and C out. So A, B, S means sum, and then C out, C in and C out. Okay, all these things will be there. And here we write the monitor command to fill up the values time wise of for this particular column. So this belong to this column, this belong to this column, and this belong to this column. So values of the columns will be filled by the monitor command, which is printf kind of, but it is a more dynamic because it scans the input over time, and whenever there is a change, it prints the values. We are using the shorthand. At 0 time, we are giving the value 0 to A, 0 to B and 0 to C in. So here we have clubbed 3 variables together. This is 3 means these are 3. B is binary because the following values will be binary. In the similar fashion, we continue the truth table here. Here I have taken a jump of 5 time unit each time. This completes the truth table. And at time unit 40, I will finish. So here you can see that here we have completed the truth table of 3 variables. We have 0, 0, 0, we have 0, 0, 1, 0, 1, 0, 0, 1, 1, and hence we reach up to 1, 1, 1. So the input truth table is captured here for this full adder, and we will get the outputs here in the simulation. Here we end our initial block, which has started with the begin keyword and ends with the end keyword. And here we instantiate our full adder from the previous slide here and we give the names A, B, C in, sum and C out as the port names. And here for simplicity, I have kept the same names. Later I will, in some other episodes, I will show you the different way you can deal with these ports. Here we end our test bench module with the end module command, right? This ends the test bench. So here we complete. So we are done here. Now let's move on to the simulators to try these Verilog codes and see how the output is coming. Hey guys, welcome back, and we are here in our directory where we have the two codes, that is for the full adder and the mux. Let me open them with Geany. Here I have kept open. So here in Geany we have mux.v. First we have the module definition, and at later part we have the test bench. So I have explained these to you, both of them in the slides. Now let me run simulation for this. Here in Geany we will use the Verilog. Let me do ls. Here you can see our mux.v is there, and since Geany is a tab browsing, I have also kept open the full adder.v in another tab. This is the beauty of the Geany, so you can keep multiple files open side by side. And here in terminal, let me run the Verilog. Then I give the module name mux.v, and then we give -o. The output file, the object dump here will be there, the output object dump which we have to execute to run the simulation. So I give it a name mux. So I run it, the run is complete, and let me do a ls. So you can see as per the run, the mux is created. The VCD file has not yet been created. Let me run mux. So you can see here in the test bench, we have defined the column names here and corresponding monitor commands to fill the columns. And we have defined vectors, that is the truth table for the cell 1 and cell 0 to be changing with time. And here we can see the output. So here you can see that inputs are checked first, whatever input we have given as port tick B0110, 0110, and then we change here, we change our output here in this column independent changing, and the corresponding here is independently changing. So at the beginning we have not set any value, so the first one we ignore here, and rest of the 4 values we will pick here, because here we have set it, but at the initial stage we have not defined any cell 1 and cell 0. We have defined here after time lag of 1 time unit, that means time delay of 1 time unit. So the first entry is x here. Let me clear. So we do not count this one because this is we have not defined, and the rest of the things we have defined, and as per our definition it is changing. The mux will pick up as for 0110. So here you can see it is picking 0110 as per the truth table operation, that is all combination of values we have put here 0001 1011. So accordingly the output is changing for the 4-to-1 mux. So here we are done with the mux related simulation in Verilog, that is the Icarus Verilog, and we are using the Geany ID for our entire operation. Now let me clear the screen here and let us move on to the full adder, right? So here you can see that your half adder is defined as we have done in the slide, and here is our full adder module. The structure modeling is done here. And you can see here, right, the test bench is here. So you can see at first we with the display and all we have defined the column names and the column values, right? And then we have defined the changes to the input, and as per a truth table we have defined the change in the inputs, 3 inputs here for the full adder A, B and C in. We have done here, and according to that the output will be displayed on the screen here when we simulate as per these statements. So let me run the simulation. Verilog, we will give the full adder, then -o. We give the dump, object dump as FA. Here, once we execute it, it has run the simulation and the object dump is created as FA, and you can see we do not have a corresponding VCD file. This VCD is from the previous mux simulation. Let me execute the full adder. And here, once I execute, you can see, right? Here the print statements have given the column names and checking the output of full adder. Don't worry, I will provide the download links of this 2.v file in the description of this video, from where you can directly download them, use them, or alter them as per your need. So here you can see the time is independently changing here, and as we added delay, right, it keeps on adding. So this is added to the next, and this is added to the next, and this way at here it finishing, right? So you can see at 140 it is finishing, and whenever the values change as per our truth table change here, right, we have defined the truth table for these three inputs, right? So A, B, right, and C in, right, these are inputs, and this is our output S, and C out is our output. So the change here you can clearly see as a truth table. So this way you can verify the functionality. Let me show you the graphical output also here. Let me clear it and let me show you the GTK-Wave. First we have done the mux, right? So here is the mux one, and the VCD is here. So let me launch it. So here you can see here it has come, right? All the inputs are here, and you can see the types which we have defined here, right? You can see the type definition in Verilog is also coming here, and we have the all signals and all wires and interconnection is coming here. So from here, if we want to select anything, that will come here, and the corresponding waveform will be shown here. Let me show you. So here are 4 inputs, 1, 2, 3, 4, right? These are inputs, and we have 2 selection inputs. Since we have not given anything at the beginning, right? You remember the X from the terminal simulation, and here is our out. So let me expand it and fit it in the screen. So here, if all these inputs you want to check the value, right, you can click a cursor and take the cursor at some point, and there you will see the corresponding values, that is 1010 values will be displayed here. Let me move it to some other point here. So here, as I am changing, you can see the changes are automatically coming here. So as I change again, you can see changed, right? It has changed here from the previous one. So this way also you can verify the operations in form of waveforms. So these are called waveforms, and these are digital waveforms, and this file is VCD file. So let me close it, and here let me clear it. Let me do alias of .vcd files. So we have another full adder, right? We have shown for the marks, right? We have the full adder, right? So let me launch the full adder. So here you can see the full adder is here, right? It has also a half adder and a half adder. So if you want to check for the half adder, you can go ahead and check for their values also. Half adder 1 and 2, right? You will see all these things. For half adder 2, you will also have the other values. So you can go and debug, right? Here is the full adder, right? You have the A, B, also the wires, and there is C in, right? Internal C1, C2, and S1 is also there. C out and sum, right? So all these are there, right? Select and delete all. So here, let me check the final output here. A, B, C in, and the sum and C out will be at the output. So let me expand it, and now if I put my cursor anywhere here, you can see the corresponding binary values are also displayed here. Since you have not given print of the internal variables, right? What you can do, if you want to check what is happening in the half adder, so you can put all the internal values right here, and then half adder 2, all the values here. This way you can investigate the values at any time of your circuit if you are facing any kind of anomaly in the expected output. So here, say if you see something difficult here, right, what you will do, you will put your cursor here, right, and then you will check the values here, what is happening, and you will check, okay, this is happening at 1 and this is happening at 2 of the internal circuitry, right, for the half adder 1 and half adder 2. So this way you will investigate the things inside your design. So here we are done with the simulation and the waveform verification for both the mux and full adder using the Geany. Now let me close the Geany and let me move on to the Vivado. So I have opened a terminal here and let me launch Vivado. So the Vivado splash screen has come, and here we are with the Vivado home screen. So here let me click on create project. Next project, and here it will be saved in our Verilog 3 episode and Verilog codes. Next, RTL project, do not specify sources at this time. Next, category all boards 1. Next, and we here finish. So here the Vivado interface is ready, right? Let me add sources. Next, add files. We add mux.v. Finish. And here you can see our mux EB and our mux module is here loaded. It is opening in editor, right? mux.v. So here you can see our test bench is there and our module is here, the definition, and the test bench is at the later part. And let me run simulation. The simulation is done. You can see here that this two has the column names and this is also the column name, and here you can see the initial input values and here the table. So first one we are omitting because in the test bench we have not done, and here you can see that we have varied the cell 1 and cell 2 output, right? And we have got the output here in this column. So somehow here the alignment of the tab is different and here the output is coming, but however from the column sequence you can understand this is cell 1, this is cell 0, and this one is output. This way you can interpret. Now let me move on to the waveform. So here I have done the zoom fit. You can see here, let me change the panes because these panes are not yet. Let me do the zoom fit. Yes. So here you can see that at the beginning this cell 1, cell 0 is not fixed. So these are red, as here it is coming as X, as here it is coming as X, right? And here it is coming as red. These are same. So don't think about them. Rather, if you click here, right, you can see the different values here also coming. If you want to debug this, you can also debug it, and you can see the corresponding value changing as per you move the marker here. The corresponding values will change here for all these inputs. So this way graphically with the waveform you can debug your design or check the functionality. And as I have said, right, mux is there, right? So here you can see all these ports, etc. And we are done with the mux simulation using this Vivado. Let me go to add sources, add files, full adder, sources, right? So mux, let me remove from this project. It has removed. So we have this one, right? Full adder, right? Opening in editor. Here you can see the full adder. First, you can see the half adder here. This code is provided in the video description from where you can download it and you can try it at your end. Here is the full adder, the structural modeling of the full adder using the half adders, which we assume that we have received from a vendor. And finally, we do have the test bench here, right? I have explained in detail already. And here, if you go, right, let me run the simulation. So let me control the panes here and let me do the zoom fit. Here you can see the inputs and the binary values are coming, right? And if you put the slider here, right, the corresponding binary values will change. And here you will get the change values of these binary variables. So this way you can debug your design anomaly. If something, say if at this point the anomaly is coming, you will put your cursor here, and at this point, once you put the cursor, the values will change here, and according to that, you can debug your design. Another thing, this is the graphical, and also we have at the bottom the, let me open the test bench side by side here. You can see, right? So all these display related command, the printf type of command is creating first set of column names and etc. And then the truth table creation by the value assignments right here. It is creating the truth table here. So here you can see that the time has gone and some has shifted here. However, this was not the case in the previous simulator. This is time A, B, S, C in and C out. So this way you should interpret them. So now you can see all these codes are simulated in both the text fashion here and as the waveform here. You can take either this approach or this approach, or you can use both of them to understand whatever you want to debug or go deeper in the design. So we are done here with the Vivado simulators, and we have simulated both the marks and full adder here, and we are done here. Thank you very much for watching up to this point, and don't forget to like, share and subscribe. In case you have some dislikes, put that in words in the comment section down below, and bye for today.